hopefully you've remembered Jed's BIDE equation that he mentioned in lecture. To calculate the number of individuals in time step 1, we're simply going to start with those individuals, and then we're going to add the births, that's B, plus we'll add the immigrants, so we'll not follow our columns here, but we'll follow the notion of BIDE. So there's our immigrants. Then we'll subtract off the deaths, and we'll subtract off the immigrants. And that gives us our next time step at time step 1. And you can see that our graphs that we've sort of pre-set up for you are starting to be filled in here. For the sync, it's the same thing. We start off with the number of individuals, and now we're going to add the births, add the immigrants, subtract the deaths, and subtract the immigrants. And at this point, we can pull everything down. And if there's a mistake that's made, it's because we've missed an anchoring someplace. And I think that the anchoring problem is right here where I forgot to anchor the reference to the carrying capacity. So I'm going to move that up and anchor this. At this point, we're able to calculate lambda for the whole system, and that is simply going to be the whole population at time step t plus 1 divided by the population in the previous time step. And so for this particular system, we've experienced a 5% decline. So lambda, if you can remember, the lambda value of 1 means the whole population is stable. Lambda values less than 1 indicate the population is declining, and lambda values greater than 1 indicate that the population is increasing. And these are all related to the R parameters that Jed talked about. And I put a little text box in here to remind us that capital R is the geometric rate of increase. We're going to calculate our growth rates the same way. It's the same thing as the geometric rate of increase, and then we will also calculate lambda. We're going to calculate these outputs for our year 200 outputs, just in case this thing needs some time to stabilize. So at this point, we can take all of our equations and copy them through to the year 200. And we can see our dynamics playing out in the figures that are displayed. So what happened here? Well, let's focus on the source. So here is the red line represents the source. The source has a birth rate that exceeds the death rate. It starts off well below the carrying capacity. As time goes on through years, the population increases as we expect it to, but once it hits 100 individuals, it levels off because we've forced those individuals that are beyond 100 to move into the sync. Let's see if we can track where that happens in the sync population. The sync population starts at 50 individuals. It has a birth rate that is lower than the death rate, and so it is expected to decline through time. And we see that that in fact is happening. Right about here, though, it starts to grow again. It starts to increase. And why would that be? Well, it occurs at the same place that the source reaches the carrying capacity and begins exporting individuals to the sync. So we see the sync start to take off as well. And in this particular model, the sync also stabilizes. How about the total? The total started off at 100 individuals. Then it actually dropped a little bit because the sync was losing individuals faster than the source was gaining them. So the source rate of growth, it's gaining, if we just figured these were isolated populations, this is an increase of 0.1 individuals per individual per year. here's a loss of 0.2 individuals per individual per year. So it's going to decline faster, but over time we see that the population begins to pick up and eventually stabilizes again, and our whole system stabilizes at roughly 150 individuals. Now we can calculate our geometric rate of increase, or R. Now remember, in the past we had talked about R as being just the birth rate minus the death rate. Well, here we have to consider some other rates as well. We have to consider the immigration rate and the emigration rates to the source and the sink. And you can see that we've plotted these rates, and these rates are also changing through time, but they do stabilize. So what rate should we use in cell E3 to represent the emigration rate of the source, and what should we use for the sink in terms of immigration? Yeah, we should use something where the population has stabilized. We don't want to use something here because we know that these dynamics are not at some sort of equilibrium level at the very beginning of our simulation. So let's calculate the emigration rate for the source as the very last entry down column G. And then let's calculate the immigration rate to the sink as the very last entry down column M. Now we can compute the geometric rate of increase for the source and the sink by simply using the BIDE parameters. For the source, it's going to be the birth rate plus the immigration rate minus the death rate minus the emigration rate. And for the sink, it's going to be the same. The birth rate plus the immigration rate minus the death rate minus the emigration rate. And again, I have a little typo. Sorry about that. So we see that the growth rate at the end of our simulation is 0 for the source and 0 for the sink. It means they're not changing. Here we can represent these same things as a percentage. So we'll just, these are highlighted and they're formatted as a percentage, and so we can just express that same result as a percentage. So these have no growth. They're remaining stable over time, even though the source is happily pumping out excessive individuals and the sink is happily receiving them. Now we've calculated lambda down column S for the whole system. We can also ask, how does the population change within the source and sink itself? And that is just going to be R plus 1. We learned that from a previous exercise. So here you have it, a very, very simple source-sink model. Let's review some assumptions we've made. First, we said it's a female-only model, and that all females can give births. So there's no age structure in this particular model. Remember that the source was defined as a subpopulation where the births exceed the deaths, and the sink is a subpopulation where the deaths exceed the births. In this model, we've assumed that the source has a carrying capacity, meaning that not all individuals can have access to high-quality habitat. There's a limit to that. And once that carrying capacity has been reached, the source must send individuals to the sinks. It becomes an exporter of individuals, and the sink becomes an importer of those individuals. Now it's clear to see why you would conserve a source population, right? Because it's very good habitat, and it's the production. It's where this population is getting its individuals from. Does that mean that sinks have no value? Well, if you think about it a little bit, these sinks play a huge role in keeping this whole system going. If we look at this particular setup and focus on the sink columns, the sink is contributing an awful lot of births to this system. If we took this sink away, then we'd be losing this many more individuals to the greater population each year. Also, the sink is a storehouse of individuals, a good backup plan, if you will, in case something happens to the source. It's true that if we set the source population and cut off the ability to send immigrants, or made this carrying capacity very, very high, our sink would eventually decline through time and go extinct. And in fact, it's a little bit hard to see this in this figure, but we started off with 50 individuals, and then our population dropped down. It basically went extinct. But then you can see, following the green line, that it came back to life again. And it came back to life as soon as our source population hit this very high carrying capacity we set, and then it became a net exporter again. And you see that the population jumps at that point as well, because the sink is now becoming a storehouse of those excess individuals. So you can probably see why the source sink framework has become such an important paradigm in conservation biology. We have a lot of populations that seem to have some kind of spatial structure, and we also know that habitats really vary in their quality. And when we think about source and sink systems, we often try to think about preserving the source, but there are also important reasons for keeping sinks around as well. And with that, we'll head back over to Jed, and I'll also be talking to you more about this model in the sandbox. We're going to really give this exercise and this model a run for its money, and really explore what the implications of source-sink dynamics are in the sandbox. So we'll see you there.
Thank you, Terry. I hope you found that exercise helpful in terms of understanding source populations, sink populations, the dynamics between the two, and how that translates into population levels, population sizes for a greater population here that may consist of one source and one sink, or perhaps multiple sources and multiple sinks. So the source sink model here, the source sink approach, has been applied to a number of different species to describe their population dynamics, and it's been pretty effective. But I will say there is some criticisms to source sinks. One of those is that it requires a lot of information about the species' natural history, or the species in question. It requires very detailed information on the bide characteristics, and again, some other components in their natural history. And some argue that it's very difficult to collect that information. It's rarely readily available on an ongoing basis, which to some extent I think is a fair criticism. I'd also note that in some cases we find that source sinks are not always constant, right? We've kind of assumed now that sources and sinks and these systems kind of remain the same over time. But that's, again, not always the case. We find that sometimes sources on a temporal basis can change to sinks, and sinks can turn to sources. So it's very difficult in some instances to capture the sort of changes in sources and sinks and really what that means. So for example, you can imagine a situation involving, let's say, plant germination. We may have plant germination in our source population being really robust because these are relatively moist areas. And we may have a sink population nearby that's very dry, and because it's dry, it just doesn't do that well. Plants don't germinate well. And you can imagine a huge now rainstorm comes through one season and really waterlogs that source habitat, which is already pretty wet to begin with, and it becomes so waterlogged that these plants just simply can't germinate. In this case, we've had roles reversed. We've had that source become a sink. Our drier habitat now, which normally doesn't do very well, is now quite moist because of this rain, and plants start to germinate at higher rates than what we'd expect. So here you have again a flip-flopping occurring. So there can be temporal variation that it can occur in these source sink systems, and sometimes that's a real challenge to get a handle on. So with that said, I think we've covered a fair amount of information related to source sinks and source sink dynamics in this module. So to wrap up, let me cover a few of just, again, the basic points, which I'll reiterate. Source populations have a greater amount of births than deaths. And those source populations reach a point at which they hit a carrying capacity, and when that happens, they essentially are sending out those surplus individuals that are being produced in that population, because these populations have a positive growth rate, a positive trajectory. Those source populations then oftentimes are referred to as being net exporters of individuals. Sink populations, on the other hand, are quite the opposite. They're net importers. So a sink population has fewer births than deaths. So these guys are on a negative trajectory. They would go extinct. They would swirl down the drain of our sink to extinction unless they received individuals from elsewhere. So if we can understand the dynamics between sources and sinks, we can then make some decisions about how to manage the population as a whole. And so we've run through a modeling approach that allows us to capture the behavior of a source and a sink to figure out how many individuals we'd expect in our greater population at large, and how that population might change over time, its dynamics over time. So with that said, I hope you've got a pretty good understanding of what a source and a sink is, how to model source-sink dynamics, and how it may be relevant to species conservation and management.